Okay, so hi Year 12s. So I'll be making the video for the subtopic 3.2, alcohols now. Now, when you look at alcohols, pretty much you're just going to be looking for the OH group. Now, depending on the priority of the different groups that you might find in a molecule, the molecule may actually be an alcohol, or it actually may just have an OH group substituting a different functional group. But for Year 12, if you see an OH group by itself, so no other things like a carbonyl, like a C double bond O, then you're probably going to be dealing with an alcohol. Now, they do have the suffix of ol, so actually while I'm here, I'll just get the little LED pen going again. So you'll see the suffix ol at the end of our name. So for example, if you start with an alkane such as butane, then if you were to take that and chuck an OH group on the end, you'll end up with a butanol. Now, as with any other molecule with a functional group, you do need to specify where exactly that OH or that substituent is, so the functional group is. In this particular case, because our OH is at the end of our molecule, it is going to be butan 1-ol. Now, there is an option for naming it slightly differently. So the accepted name, or the more accepted name, is butan 1-ol. But if you were to write 1-butanol, that would also be correct. Maybe slightly less correct, but it doesn't matter, it's accepted. Okay, now I did mention up here, not that it's super duper important, but when you are making an alcohol, or as in at least drawing one, they are going to have numbers that tell you where that alcohol group is. That is only if there are more than one, or there is more than one option for where that alcohol can go. So for butanol, the OH group can go on butane here at the end, or it can go in this carbon here. Now, if it went on this end, it would be the same as this end. If it went on this carbon here, it would be the same as that one there. So there are only two options. So you'd have 1-butanol, or butan 1-ol, or you'd have 2-butanol, or butan 2-ol. When you look at methanol and ethanol, whoops, I don't know why that happened. When you look at methanol and ethanol, there is only one option for the OH group, so they don't have any numbers. Okay, as we scroll down, when you have alcohols with alkyl side chains, or when I might say alkyl side chains, just a reminder, we're talking about just the hydrocarbon side chains. The same naming scheme applies for just the plain hydrocarbons. We are going to number the carbons. This time we need to consider the most or the functional group with the highest priority. In this particular case, most of the molecule is just plain old hydrocarbon, and that's the lowest priority. The OH takes priority, so the molecule will be called an alcohol. Not only that, but the numbering scheme for that alcohol will try and keep the number the smallest for the OH group. So in this particular case, we are not going to count from this side to get 1, 2, 3, 4, carbon 4 for the OH group sticking off of it. We are going to start from the left because that will give us the lowest number. So as you can see here, we have our 3-ol, which is the ending of our molecule name. Now we just need to name the rest of it. So I'll use some blue pen to hopefully show up a bit more clearly on this pink highlighter. We need to do the exact same thing as normal, which is count the longest chain of carbons. So we have 1, 2, 3, actually I'll use this again, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. Now I deliberately chose to draw this one with the what looks like an ethyl group sticking off the bottom, but because even though it's sticking at the bottom, doesn't automatically make it a side chain. In this particular case, it's actually part of the main longest unbroken chain. So this is actually our substituent. So we have our 1, 2, 3, 4, 5, 6, 7 carbons. That makes our molecule. Oops, sorry. Oh no, what have I done? There we go. I was going to try and erase it, but it would erase the highlighting as well. There we go. 7 carbons, so it's hep 10 3-ol. Now it does have a substituent, so that is this carbon group here. It is a methyl. It is a methyl because it's only one carbon, and the number of the carbon number it's on will be based off of the numbering scheme that we started for the OH. So in other words, the 1, 2, 3 that I've put here, we have to continue that. 4, 5, 6, and 7. We cannot just decide to count from a different side just because we want to minimize the number for the methyl. Once you've minimized the number for the alcohol, so this number here, then the other numbers just fall out wherever they lay. In this particular case, we have our hept. What am I doing? Oh, I'm getting... Things are not working very well out today, are they? Let's just fix some stuff up. So let's scroll down. This is actually not hept-3-ol, it's heptanol. There's probably a reason why I gave us so that much space. Regardless, we all make mistakes. Nothing that can't be erased. Now, so we've got heptan-3-ol, and we're going to relabel our carbons. This is what happens when I can't just erase the thing, what I've written, just so I can save myself time and not have to redo that highlighting. Okay, so we have heptan-3-ol, and we have a methyl group on carbon number 5, so it will be 5-methyl heptan-3-ol. So it looks pretty complicated, but once you break it up into this little chunks, hopefully it makes a bit more sense. Okay, let's continue. Now, if you have more than one hydroxyl group, the OH group on a molecule, then not only do you have to put a number to tell you exactly where each of those OH groups are, but you also change the ending from ol to a number, so another word depending on, or you add another prefix depending on how many OH groups there are. So if there's 2 of them, it'll be a diol. If there's 3, it'll be a triol, tetraol, and pent, etc. Now, we are going to ignore these ones. First of all, now that I look at it, I'm not completely sure that my name is given there, but regardless, not a big deal. You won't be having to name anything with more than, at max 3 probably, 3 alcohol groups. Regardless, so if we look at these examples, if you see this molecule here, you do the exact same thing as normal. You go 1, 2, 3, 4, 5. That'll give us our pentane bit. Now, just before I continue, there is a bit here that I've written that should be read carefully. Normally, if you are going to have just one hydroxyl group, you're going to remove the E from the end of our alkane name. So, for example, up here we have heptan-3-ol, not heptane-3-ol. Up here earlier we had butane becomes butan-1-ol. It is because this ol is a vowel. If you have a vowel here, you remove the vowel at the end of the butane name. Now, once you are talking about a diol or a triol or a tetraol, you now no longer have that vowel in between the base name, as in the base hydrocarbon name, and the suffix, the diol. So you will replace the E. So in this particular case, it'll be pentane diol with some numbers in between that tell you exactly where those two OHs are. In this particular case, if we count 1, 2, 3, 4, 5, we have 2, 4. If we were to count from the other side, we would also have 2, 4. Now, as I said, and I've said previously, you must have 2 numbers if you have a diol. You must have 3 numbers if you had a triol. Even if both of the OH groups are on the same carbon, then you still need to have those 2 numbers. So in this particular case, we have our pentane diol, and the numbers in between are going to be 2, 2, that describes the carbon number that those OHs are both on. Now, like normal, I know I probably shouldn't need to say it, but if we start from the right, 1, 2, 3, 4, you could say pentane 4,4 diol, but you would be wrong because you need to minimize those numbers. Okay, so just to summarize in that little bit, because our suffix has a D, which is a consonant, not a vowel, we would put the E back on. So instead of pentanediol, it's pentaneediol. Okay. Now, when you have alcohols, they can be classified as one of three. So we have primary, secondary, or tertiary alcohol. Now, I'll cover exactly what they are in a second, but the reason why we actually bother to categorize them is because they actually undergo reactions in different ways. So, knowing that, if we look down at these three structures here, you see our primary alcohol on the left. If you look at the alpha carbon, now the alpha carbon is the one that's directly attached to the OH. In this particular case, we have our OH directly attached to this carbon here. That is our alpha carbon. Now this alpha carbon here, you need to ask yourself how many carbons are directly attached to that one. And you can see in this particular case, it goes straight up to here, it's only directly attached to one, and it has a bond to the OH obviously, as well as two hydrogens. Now the degree, so primary being first degree, is telling you how many carbons that alpha carbon is attached to. It probably seems a bit complicated, but with practice hopefully it'll be a bit clearer. This secondary one here, the OH is directly bonded to this carbon. Now if we look at how many carbons that is directly bonded to, we see one on the right, one on the left. And obviously to make up our four bonds, we've got that bond to the OH that we started with, and an extra hydrogen that is not visible normally in these structures. Now thirdly, if we look at our tertiary one, we can see our OH is directly bonded to this carbon here, and that carbon is bonded to one up to the right, one up to the left, and one down to the left. That is our three carbons, that's our tertiary. There are no hydrogens on here because this carbon here has 4 bonds that we can see, so there are no hidden ones to hydrogens that we need to worry about. Now, as I mentioned a moment ago, the degree of those alcohols is important based on the reactions that they do. And the reason why it matters is actually because of those hydrogens that are either there or not there, depending on whether we're looking at the primary, secondary, or tertiary. When you do a reaction with these, you will often be messing with the bonds to the alpha carbon. You'll often need to remove something to replace it with something else. An example which we'll talk about before is we actually remove one of these hydrogens to make a double bond with the oxygen. Now, carbon groups like this one here are actually relatively strongly attached to this alpha carbon, so they're very hard to remove. On the other hand, these hydrogens are they're not easy to remove, but they're relatively easy to remove. So if we have the right reaction conditions, we can remove this one or this one, and which will allow us to make a new bond with our alpha carbon. Because our tertiary has no carbon-hydrogen bonds, it only has carbon-carbon, as well as obviously our oxygen here. We can't break any of these three bonds, or these three bonds here, to make a new one. Oh, actually, that's not quite true. You can do it, but not under the reaction conditions that you need to learn about in stage 2. Okay, so we are going to go over some of the, one of the reactions that we have here, and that is when you react acidified dichromate, which is our H plus Cr2O7 2-. So usually it's made of potassium dichromate mixed in acids such as sulfuric acid. Regardless of what it's made of, when you react them, you are going to remove one of these hydrogens and the other hydrogen off the alcohol and make a double bond here, as you can see for this structure here. Now, this one here, we have not covered this molecule yet, but this particular functional group with the C double bond O, the C double bond here, O here, and the H with another carbon group, that will be an aldehyde. And that will be one of the later chapters that we look at. Now, I've put a little star here, so if you look over here, this R group here could be anything. Now, it says here for methanol, first, second, and third degree are not relevant, but it reacts identically to a primary in this case. Now, if you have an R group that is a hydrogen as well, then obviously, if we have a methanol, we've got that carbon attached to no carbons. It's not primary, but either way, it will still react the same way because we have only we have lots of carbon hydrogen bonds we can remove to do this reaction. So you'll still get an aldehyde. This is the very smallest type of aldehyde if we have methanol as our reactant. Now, moving on to our secondary. So if we have a secondary here, we can remove this hydrogen here, as well as the hydrogen on the OH, and make our double bond, as we see just here. The deal is here, though, is that our final molecule has a carbon group on both ends, and so there's no hydrogens left. And we call these, because they do behave differently in different situations, we call them ketones. And again, we will cover them in a later chapter. Now, as I mentioned before, because our tertiary alcohol does not have a hydrogen attached to this alpha carbon, so this is the alpha carbon, it will not react with acidified potassium dichromate. You can't lose that hydrogen if there is no hydrogen, and these carbon-carbon bonds here, here, and here are too strong to be broken by this particular set of conditions. Cool, as I mentioned just here. Okay, now there's not much left here, but just so we know, over here for our primary alcohol that reacts and makes an aldehyde, there is a further reaction that can occur, and that again is mainly because we can oxidize this OH bond, so we can do another step with that one. For our ketone, there is no carbon-hydrogen bond that we can do another further step with, at least again in the reaction conditions that you need to worry about in stage 2. So as I said here, if you take our primary alcohol, you react it in 2 steps, so you oxidize it a second, you oxidize it further, what you end up with is a carboxylic acid. So this carboxylic acid, again, this is a functional group that we'll be covering later as well in 3.4. But yes, so sometimes we'll get our reactions stopping at an aldehyde, sometimes they'll continue on through to a carboxylic acid. Again, it depends on the conditions. You don't have to know exactly, you just need to know that it can occur. So let's have a look here. Let's do another example. So if we take this alcohol here, it is a primary alcohol. That means that we have two little hidden hydrogens there and there. If we were to react it with acidified dichromate, now I know I keep saying acidified dichromate and acidified potassium dichromate interchangeably. They are the same solution, it's just the potassium is what you use to make the solution. It just doesn't really, the potassium doesn't really have much to do with the reaction itself. Regardless, if we do this, we're going to take our base molecule and we're going to keep that bond with the oxygen, but we're going to make it a double bond instead. And we can leave this structure looking like this, but what you can also do is you can also put that hydrogen on that will be there as well. I might, just for the sake of making it look a bit nicer, I might remove it. That there, where you see your C double bond O group at the end of our molecule, that is an aldehyde. Cool. Now, as I said before, that can undergo another reaction because of that hydrogen sticking off there. And what we can do is we can make it into a carboxylic acid, where you take that C double bond O that we had already, and we remove the hydrogen and we attach an OH group to that. This is a new molecule with new properties that we've made from our original primary alcohol. Now, if we look at our this one here, let's have a look directly at our OH bond directly to this carbon here. This one is the alpha, and it's attached directly to 1 and 2 carbons. So that makes this one a secondary. Now, that means it will react with our acidified dichromate solution to make, in this particular case, I'm just going to draw the base, this base chain first, and then off of the third carbon from the right, we are going to replace it with that OH bond with a double bond O, and that is a ketone. That does not react further with the acidified potassium dichromate, and so it stays just there. Again, the reason is because that carbon, this carbon here, now has all of its bonds filled. 1, 2, 3, 4. There is no carbon-hydrogen bond that could be removed to further oxidize this. And I think that's pretty much it for now. We will use this knowledge to combine with other bits and pieces of information later for our, our esters and our triglycerides and stuff like that. But for now, I think we're all done. Cool. Hopefully this was enlightening.